Let's wait for 2-3 minutes for others to join, and I'll set up the screen. Is this visible? The slides?
Yes, it is.
Okay, perfect. How do I get rid of this? Okay, so I guess most of you have joined, those who wanted to join. So we'll start. Welcome to the second week of the classical mechanics course. For those of you who are joining for the first time, we are meeting every Tuesday, 6 to 8 p.m. and essentially we are going to solve some problems from previous year's assignments, and you can ask me the doubts that you have had during the week's lectures. So this week there are only two questions from the previous years that I could find. So I thought maybe we can start with a recap a brief recap first. So we'll just see what happened in the week, uh, and I'll write down some of the things that we learned, and you can stop me whenever you want to if there is any questions in that portion. So recap. So first we learned in the first week D'Alembert's principle, which was the sum over all particles mi double dot minus fi dot delta ri is equal to 0. These are like vectors. Okay, so this was your virtual displacements, and these are actually force, and not that fi minus this mi ri double dot, the thing in the bracket, need not be 0, because there can be forces of constraints, forces due to surface. And another way of saying that is that this delta ri could be in principle dependent on each other. So we have to first transform it to generalized coordinate, and then we can say that whatever coefficients are there are 0. So when you do that, you discover that there is a quantity called Lagrangian, which is a function of generalized coordinates, generalized velocities, and could be function of time, and that satisfies an equation called Euler Lagrangian equation, del q dot minus del L by del Q is equal to 0. So this is called Euler Lagrangian equation. In general, the more technically it should be Euler Lagrangian equations, because for every degree of freedom you have one equation. Right? Alpha could be from 1 to whatever degrees of freedom you have. Okay. Uh, then we saw some examples, etc. One very important thing we noticed was if L does not depend on some Q alpha, then Q alpha is, we call it, if this is 0, then we call it cyclic, and it means that conjugate momentum corresponding to Q alpha, which is defined as dou L by dou Q alpha dot, is 0. Not, sorry, not 0, it's conserved, constant. So for every cyclic coordinate, you have one constant of motion. Uh, then after some examples, we learnt about Euler's theorem. Can someone tell me what was the statement?
The statement was if you take a function f of some x and y,
Yeah,
then x times the partial of f with respect to x plus the partial plus y times partial of f with respect to y will be equal to the function itself. I mean the degree of the function n times
n
f of
times,
xy.
right,
Yeah.
where n is degree of homogeneity. Okay, so just to modify your statement a little bit, f of xy has to be a homogeneous function. Function of degree n. Then this statement is true. In general, you can have as many coordinates as you want. Okay. Then we saw that the kinetic energy term, which is half mri square, right? Sum over I, can be converted into QIs. So when we convert into generalized coordinates, we can have terms T0, T1 and T2, where T2 is quadratic in velocities, this is linear in velocities, and this doesn't depend on velocities. So we can have these three kinds of terms, and then we can apply the Euler's theorem, and we'll get that T0 when we apply Qi dot T0 Qi dot will be 0. When T1 applied on this will give 1 times T1, and T2 would give 2 times T2, right? So, and after, by calculating total derivative of dl by dt, we found that there is a quantity which we defined as Hamiltonian of the system, which is q alpha dot delta L by delta q alpha dot, and this is your conjugate momenta minus L, and that satisfies some property, which is that total derivative of Hamiltonian is negative of partial derivative of time derivative of Lagrange. So, which means if Lagrangian does not depend on time, then your Hamiltonian is conserved. So then we saw some, then we calculated using the Euler's theorem these three facts, what H would be, and in general, H is T2 plus U is your potential minus T zeros, and then if we have Ri as functions of your generalized coordinates, but if they do not explicitly depend upon time, then T becomes T2, we saw that, and then in that case H becomes T2 plus U, and T2 is T, so it's T plus U, so total energy. So yes, the Hamiltonian is the total energy, but only when this transformation does not explicitly involve time. So that's that. Then again we saw some examples of bead rotating uniformly uh, on a wire that is rotating uniformly in horizontal plane, and then we saw an example of two masses connected with spring, and then we found that there is some cyclic coordinate, and basically found that center of mass moves with constant velocity. That is what we expect from Newtonian mechanics. So that is almost what happened during this week. So if you have any questions regarding this discussion, ask right now. Anyone? Hello? Okay. If not, then let's solve those two questions. So the first question is super easy. The Lagrangian is given of a free particle in cylindrical coordinates is given as half rho dot square. Rho is the radial coordinate from the z-axis, plus rho square alpha dot square. By alpha they mean the usual phi, the angle with respect to z-axis, plus half m z dot square. Which of the following is not a cyclic coordinate? So, can someone answer this?
Rho.
Rho will not exactly coordinate.
Rho is not a cyclic coordinate. Okay. And why is it so?
Because the term rho square appears in the Lagrangian.
Right, right. So the definition is that the cyclic coordinate should not appear in the Lagrangian. Well, not exactly. The more technical definition would be that dou L by dou Q dot should be 0. So, sorry, my bad. Just Q should be this. Should be 0. It can happen like in a rare scenario that it appears twice or thrice in different terms, but when you take derivative, it's 0. So it still does not depend on Q. So then Q is cyclic. So since with respect to rho, the L is partial of L is not 0, we can say rho is not cyclic. So the answer is rho. Okay. So which coordinates are cyclic? The other two, right? Because you can see there are no alphas or z's in our expression of L. So alpha and z are cyclic, which means the corresponding p alpha. This is extra, by the way. We got the answer, but we want to find the corresponding momenta, conjugate momenta, because they would be conserved or conserved. So let's first calculate P alpha. Can someone say what P alpha would be? So the definition is partial of L with respect to alpha dot, right? Anyone?
M rho square alpha dot.
M rho square alpha dot. That's right. Because we have rho square alpha dot square. So when you take derivative, it will become 2 rho square alpha dot, and then you have this 2 in denominator, so that cancels out. Okay. So what is this? What is this quantity in physical terms?
Angular momentum.
Angular momentum, because rho is like r from the z-axis. So if you imagine z-axis, this is your rho. This is z-axis, and this is your rho, and alpha dot alpha is the angle. This alpha. So this is like omega. So entire thing is m r square omega or I omega. So this is your angular momentum, which is constant. So this is saying that angular momentum is conserved. And the second momentum, that is the conjugate momentum of z, that would be partial of L with respect to z dot. That would be m times z dot, which is thus angular momentum along z axis. Okay, so these two are constant. Okay, let's go to the second question. Is this clear to everyone?
With angular momentum, not linear momentum along z.
Sorry.
You said it's angular momentum along z. Wouldn't that be linear momentum?
So yeah, this will be angular momentum along z axis, right? Lz.
Yeah, I meant the second one, pz.
The second would be pz, right? Because it is m times z dot. So m into vz. So this is your linear momentum. Sorry, did I say angular momentum?
Yes, you said
Oh,
angular
sorry,
momentum.
my bad. This is linear momentum along z axis. This is the angular momentum. Sorry, my bad. Thank you for correcting. Okay. The second question is Lagrangian of a system is given by half ml square q1 dot square plus q2 dot square and then minus half kl square q2 minus q1 whole square. Okay. So can someone say what kind of system is this? Which physical system would it represent?
Spring connecting two masses maybe.
Right. Spring connected with two mass. And what would be the length of that spring? The natural length of the spring? Anyone? So if the natural length is A, then the energy is half K and extension. So what would be the extension? It would be, let's say this is x2, this is x1. So it will be x2 minus x1 minus A square, right? So here we don't have any A, which means its natural length is 0. So it's a just spring without any natural length. Whatever by whatever amount you extend, that is your energy. So when A is equal to 0, it becomes half K x2 minus x1 square. And then we have normalized it with respect to L. So we have written x is equal to L into Q. So that Q is now dimensionless quantity. So it becomes half K L square into Q2 minus Q1 square. Okay. So this is your potential, right? This is T minus U. And T is half M. This is x1 dot square and this is x2 dot square, right? So that's your system. Now they are saying re-express the Lagrangian using this transformation. Q1 is some number times capital Q1 plus Q2 and Q2 is proportional to Q1 minus Q2 with the same factor, right? So if this was your gate or net question, you should realize that there is Q2 minus Q1 here. So and if we can express Q2 minus Q1 using just one variable, then the other variable would be a cyclic coordinate. That is what is asked here. What is cyclic coordinate? So how will you get Q2 minus Q1? So if you write Q2 minus Q1, it becomes, we can take out this square root of 2ml square outside, and it is Q1 minus Q2 minus Q1 minus Q2. So it will become minus 2 Q2, right? So it is minus of square root of 2 ml square Q2. So this term is Q2 square, and this will have Q1 dots and Q2 dots and nothing else because they are just linear combination of those two, right? So there is no Q1 in the expression of Lagrangian. So as someone pointed out in the earlier question, Q1 would be your cyclic coordinate. And so if we want to formally write, then we can first transform the Lagrangian of ml square and q1 dot square plus q2 dot square. So both of them will have factor of 1 by 2 ml square, right? Then q1 dot plus q2 dot. So q1 dot would be capital Q1 dot plus q2 dot, and this will have this dot q1 dot minus q2 dot. So when you square and add, the cross terms would disappear, right? One would have plus and another would have minus. So it will become 2q1 dot square plus 2q2 dot square, right? And minus, as we saw, half kl square. q2 minus q1 is 2 by ml square times q2 square. So this ml square is cancelled. This one factor of 2 is cancelled. So you get q1 dot square plus q2 dot square by 2 minus k by ml square q2 square. Is that correct? Yeah. Okay. And clearly it does not depend on q1. There is no q1 in the expression. So partial of L by partial of uh, capital
The
Q1.
Lagrangian will have a positive sign for the it will be plus k by ml square q2, I think.
Why do you say that?
Q2 minus q1 has a negative sign, correct? So when you substitute it,
Mm-hmm.
it will turn the negative into a positive, correct?
But it's square.
Or okay, I missed out this square. Sorry, my bad.
There is square. Yeah. Okay. And okay, so q1 is the cyclic coordinate. Okay. And what would be the, whenever you see the cyclic coordinate, I just want to put habit into you that whenever you see a cyclic coordinate, you should try to calculate the momentum, and that would be partial of F with respect to q1 dot. What would this be? Harish, can you answer?
It's again Q1 dot.
It's just q1 dot, right?
Yes.
So q1 dot is equal to 0, which means sorry, I keep on making the same mistake. This is constant. So q1 moves with constant velocity. Okay. And what is q1? That is small q1 plus small q2. So that is the center of mass, because both masses are equal. So again, nothing surprising, right? So these two were the questions. I have some more questions if you want me to solve. And if you have any questions, ask me.
Yes, I have one question.
Yeah.
In fact, two. So the first one is in a famous double pendulum problem.
Mm-hmm.
Why are we not considering the potential due to the masses, like the gravitational potential between M1 and M2?
Okay. So yeah, two things. So when we consider a double pendulum, we consider these to be rigid rods, right?
Yes.
Yeah. So the length of this and length of this are supposed to be constants. So even if there is any attraction between these two, the tension in the rods will take care of that. That is the assumption. Now, how good is that assumption? We know, right? When we attach two masses, reasonable masses, if they are not neutron stars or anything, the rod generally doesn't break, and the extension or the compression in the rods is order of millimeters, so micrometers. So whatever the Young's modulus is, I'm sure you can calculate that. So that is negligible. That is one thing. Another thing is we can just calculate the forces, right? So it would be G m1 m2 by L2 square, right? So if you put in the numbers, reasonable numbers, let's say m1 and m2 are order of 1 kg and L2 is order of 1 meter. then this is order of g, right? If this is 1 meter, this is 1 kg, order of g, which is what, 10 to the power minus 11 newtons. Is that correct?
Yes, sir.
Yeah. What's the value of g? I should know. Probably, yeah, around this. So it's really small. Like our weight would be is around 500 newtons. So this is like 1,000 billion times smaller than that. That's why we can ignore. This is all what physics is all about. Like what things can you ignore and what things you cannot. So does that answer your question?
Yes, but I'm still unsure about the first reason. Is it because the tension and gravitational field, the gravitational forces cancel out and there's no work between them, or is it just because it is negligible?
I think so. Like so, so theoretically you see, once you state that rod is rigid, it means the length is constant. And
Yeah,
once it is constant, then even if you consider the potential, it would be g m1 m2 by l2, right? And
yeah,
everything is constant because l2 is assumed to be constant, so it doesn't change anything. You are just adding a number to the potential,
like,
right?
yeah.
And that wouldn't change anything. So the second question is, how good is that assumption? And now we are going into practical realm rather than the theoretical one, and then we can argue this way. But theoretically, if it is rigid rod, then you don't have to worry about the interactions.
Okay. Suppose let's change them to charges. Then I think we have to consider the Coulombic potential, right? Because the
Yeah,
charges moving and the lengths are not constant.
right, right. So again, the same thing. You have to ask the question, whoever is writing the problem, is the rod actually rigid or not?
All right.
If the question maker says it's a rigid rod, then the discussion ends.
All right.
If it is not, then you have to know the numbers. Yeah,
All right.
right.
I have another question.
Mm-hmm.
So in a question in Landau's book, so it asked me to find the Lagrangian of a system.
Okay.
And in the solution of the answer, he writes he's neglecting all the terms that are dependent only on time. So is that a significant thing to notice? Because when I compare my Lagrangian, it is not matching because he says he has omitted all the time dependent terms, individual time dependence.
So he has ignored all the time dependent components.
Yeah, the components that are specifically dependent only on time, like they don't
And
depend on other coordinates.
okay, and so did he give any reason why they could be ignored?
No, he didn't mention that.
Okay, then I'm not sure how can you ignore them.
All right.
Um, Can you tell me the question number or something? I could look it up and maybe in the next session we can discuss.
Yeah, it's
Yeah.
problem 3 in the first chapter.
1.3 Lander.
Yeah,
Okay,
page number 11.
page 11.
Yes.
Okay, I'll look it up and let you know if I can find some reasonable explanation.
All right.
Okay,
Thank you.
sure. Anyone else? Any doubt? No one? Okay, let's solve some questions. I have a couple of them ready. Okay, so one question that I found interesting is the Lagrangian is given as e to the power gamma t m by 2 q dot square minus k q square by 2. Then one is what is the equation of motion, and more interesting, what does it physically mean? Has anyone solved this question by any chance? Okay. Okay, no, then it might be surprising. Okay, you can also simultaneously solve at your homes. So the with respect to, so we find derivative with respect to q first, let's say. What would this be? Anyone? Harish, can you answer?
Yes, minus kq e power gamma t.
Minus kq e to the power gamma t. Perfect.
Yeah.
Okay. What's the next thing we calculate? That is derivative with respect to q dot. Ramai, can you tell me?
mq dot e
M
gamma.
mq dot e to the power gamma t. Perfect. Okay. And then we take time derivative with respect to uh, of this quantity. So what would this be? Let me ask someone else. Abhiniti.
C into KQ e power gamma. Gamma into
You are not clearly audible. So first, with respect, it's we are differentiating the first term.
minus mag.
Sorry, minus or plus? Okay, maybe
Plus it.
yeah. Plus gamma mq dot e to the power gamma t, right? And then we have to equate this. So we get mq dot mq double dot e to the power gamma t plus gamma mq dot is equal to mq dot. Can we can we simplify this? Yes, we can. This e to the power gamma t we can cancel out. Okay. Sorry, did I do something wrong? Oh yeah, it should be this term, right? This is equal to minus kq e to the power gamma t. So that gets cancelled, and we are left with mq double dot uh, and just a second. Yeah, plus kq plus gamma. Let me write it this way. First gamma mq dot plus kq is equal to 0. Okay, so that's your answer to the first question. And what does it represent physically?
It looks like the damped oscillator problem maybe.
Okay, and how do you say that?
Because there's a velocity dependent term and this displacement term like a harmonic oscillator. So
Yeah. So this is your normal acceleration term.
yeah.
This is your harmonic oscillator term, and this is some number times the velocity. So this is exactly damped harmonic oscillator. So you see, just by writing this e to the power gamma t, we can get an equation that is damped dissipative. So that's the beauty of Lagrangians. If you start playing with them, you can extend the ideas. You can have many systems. Mm. So that's why they generally use Lagrangians and Hamiltonians when they are generalizing some high energy theories in quantum field theories, string theories, everywhere. What you see is the Lagrangian of standard model or Lagrangian of for string theory. They start adding quadratic terms, quartic terms, higher order terms. So that just goes to show that Lagrangian is the way to go ahead, generalize. So that's why I wanted to show you this example. Another question is, by the way, is this clear to everyone? The calculation and the interpretation. Okay. Okay, then let's proceed. Question 2. It is of spherical pendulum. Spherical pendulum is just like a normal simple pendulum, but it can do this phi rotation as well. It need not be constrained to a plane. So you have a massless rod attached, and that can oscillate anywhere. So you have a mass, and that can have some angle theta, but this could be in a plane. On that plane, let's say this is x-axis, this is y-axis, then that could be at any angle phi. So the degrees of freedoms are theta and phi. Okay. The rod is massless of length, some length L. So let's first write Lagrangian. So Lagrangian will have two kinetic energy T minus U, right? T would have two terms, one is v theta. So what would be the speed along the theta direction? So how do you calculate that? You just assume that this is theta and this is d theta. Then what would be the displacement along this? So since the length of the rod is L, this will be L d theta. In dt time, you divide by dt, that is your v theta, right? So v theta would be L times theta. Okay, but that is like this theta rotation. What about this phi rotation? So let's say again I plot here. This angle is phi, right? So it goes from phi to phi plus d phi. So this angle is d phi. So how do you calculate this distance? That won't be L times d phi, right? Because the radius for this rotation is shorter than the length. How short? So this angle is theta, so you can consider this perpendicular triangle. So this radial vector would be L times sine theta. So this delta r would be L sine theta delta phi. Let's say this is delta phi. So when you divide it by delta t and take limit delta t to be 0, you get v phi is equal to L sine theta phi dot, right? This becomes your phi dot. So this is L times theta dot, this will be L sine theta phi dot. So now Lagrangian becomes half m v theta square, that is L square theta dot square, plus v phi square, that is L square sine square theta phi dot square, minus the potential due to the gravity. So that would be its height, right? So we can consider v is equal to 0 anywhere. We'll consider u is equal to 0 this. So then it becomes mgh. Now what is the height of this mass? Let's say this is h. Then h would be, you can again consider the perpendicular triangle, becomes L times cosine of theta, right? So that is your Lagrangian. And now we just become a mechanical calculator. Calculate with respect to, so there will be two equations. Let's calculate with respect to theta. Partial of L with respect to theta would be, can someone say, because I am lazy? Ananta, you there? Okay. Harish?
L square sine 2 theta phi dot square into m by 2.
L square sine 2 theta phi dot square
M by 2 minus or plus MGL
minus or
sine theta. Plus.
plus, right? MGL
Sine.
sine theta. Okay. So derivative of sine square theta is 2 sine theta cos theta. That is sine 2 theta, as Harish pointed out. So, and then derivative of cos theta is minus sine theta. So that is this thing. Okay. Now we do with respect to theta dot. Minakshi, can you please tell, this is the expression. What would be the derivative with respect to theta dot? Okay, I guess not. PK Janani, are you there? Okay, it appears Harish, you and I, only two of us are here. ठीक है Harish, you tell me.
ML square theta dot.
ML square theta dot, because 2 would be cancelled by the denominator. Okay, and now you take time derivative.
Yeah.
So ml square theta double dot. So what the theta equation would look like? ml square theta double dot minus ml square by 2 sine 2 theta phi dot square minus mgl sine theta is equal to 0. That becomes your theta equation. Okay, what about phi? So with respect to phi, what would it be? Abhiniti? This Lagrangian, what would be its derivative with respect to phi? Hi Abhiniti, you are there? Okay, no. Harish, sorry on picking you, man. But
Yeah, no problem, sir.
okay,
It's a cyclic coordinate, so 0.
it's cyclic, right? You know why it's called cyclic?
Yeah, because it has no direct dependence on phi, and you know the momentum with respect to phi dot is conserved.
Okay, no, I mean, why is it called cyclic?
Because there's no direct dependence of L on phi. That
Okay.
is the value of phi 0.
No, I'm not asking why is it cyclic. I'm asking why is it called cyclic? What is cyclic about it?
Okay.
Why is it named cyclic?
I'm not sure.
Okay. Even I'm not sure. I just thought of that question, right?
Okay.
If I had to joke, I would say that zero looks like a cycle. So I'm sure there is a better answer. Let's find out next week. Okay. So with respect to phi dot
It's ml square sine square theta phi dot.
ml square sine square theta phi dot. Perfect. Sine square theta phi dot. Right. So now time derivative. Harish,
Just ml square sine square theta phi double dot.
that would be incorrect.
No, plus ml
Yes.
square sine 2 theta phi dot. Theta dot.
I
Plus
think it
ml
would
square.
be
Yeah.
Into
M
theta dot.
Sine 2 theta theta dot phi dot. Right.
Yeah. Yeah.
Hmm. Okay. So what would be the equation of motion for phi? This being 0, right? This is 0. So you get these two equations, super complicated. That's your answer. One thing that we can notice though, uh, remark, what should happen if we restrict this to phi, constant phi, let's say to one plane, then it is just simple pendulum, right? Then it cannot oscillate in other plane, so it becomes simple pendulum. So let's say we are restricted to a plane, then phi dot is 0. We are not allowed to change phi, basically. In that case, what would the first equation look like? Raku?
ml squared theta double dot minus mgl sin theta equals 0.
Minus mgl sin theta. Is that familiar equation?
Yes.
What is it?
I think it's just a second. I forgot right now.
Okay, that's okay. It's a equation of simple pendulum, right? This is simple pendulum. And so we have recovered the equation of simple pendulum as we should have, because we are restricted in a plane, so it becomes a simple pendulum. And so this is how, when you do some research, when you are finding out new things, it's always a good idea to check it with a simpler case. Are we able to recover the simpler case or not? By the way, okay, what happens to second equation, Harish?
So it vanishes. Xi is also there.
Yeah, so phi dot is 0. It's 0 every time. So phi double dot is also 0. So it becomes true trivially. 0 equals 0. Okay. So
The focal pendulum is a spherical pendulum, right? So to describe the Bob's-Morse, we'll need such big equations, right?
to describe what?
The focal pendulum.
Foucault polynomial. Yes, right, right. So in that you finally get an expression for phi dot, right?
Time period. For what?
For phi dot. That is yeah,
Okay.
phi dot. What is it? I don't remember. It was some number by your latitude or something. I forgot.
Okay.
So let's see. On the equator, it is 0, so time period should be infinity. So it was like sine lambda, yeah, 24 hour by sine of lambda. So when lambda is equal to 90 on poles, it would be 24 hours. And as you increase it, as you decrease the latitude, come towards equator, this time period would increase. So this is not phi dot, this is 2 pi by phi dot. That is the time period.
Okay.
So you can calculate uh, this time period for your city. Uh, in India, I calculated for Mumbai. I stay here, so it's around 73 hours. It's cool.
Okay. But we'll have another time period, right? Along the other axis.
Along what axis?
In the long, like theta dot. 2 pi by theta dot. What do we call that?
Yeah, along theta dot, it would be very much equal to 2 pi square root of L by G.
Okay, okay.
Yeah.
That will be just like a simple pendulum in some random plane.
Yeah, yeah. So if you go to some museum, I recently went to this Science City in Kolkata. If you know, they have Foucault pendulum. So if you
I remember seeing one in Ayuka, Pune also.
Ayuga Pune, yeah, there are many. So if you, I watched it for 3 to 4 minutes, and I couldn't even notice the difference in the plane because it takes very long to change the plane. So
Yeah.
and in that there are many oscillations around theta dot. So theta dot generally does not care about this phi oscillations. So
Okay.
that stays the same.
All right.
Mhm. So, but yeah, you raised an important point. Whenever these kinds of non-linear equations are concerned, there is one method called methods of time scales or something. When you have separate time scales for phi dot and theta dot, you can solve them approximately, even if you can't solve them analytically exactly. So this is something that people do. So let's say that phi dot varies very slowly with compared to theta dot. So that is something for future if you ever go to nonlinear dynamics side of physics, you will see this.
I'm very sorry, sir. Can you repeat the statement again? Because there was some disturbance here.
Yeah, so when you have some nonlinear equations like this, you very likely won't be able to solve it analytically exactly. So the next step is to solve approximately. So there are many methods for this. One of them is methods of separating time scales. So you say that one variable oscillates with some frequency, another oscillates with some other frequency that is lot higher or lot smaller than the other one. So when you are considering the variations in one variable, if it is the faster variable, then you don't consider the variations in the second variable because they are changing very slowly, right? So, so when you are solving for the fast variable, you can ignore the changes in the slow variables. Does that
Uh,
make sense?
got you, got you.
Yeah. Okay. I don't think I have anything more. Oh, last time I don't know who asked about books, so I just went to professor's first introductory lectures. So I'll just list them down for the whoever wants to use it. One is Land of Lifshitz. The giant of the field. I mean, not the field of the universe of mechanics textbooks. The second is Goldstein. As they say, it's the gold standard of classical mechanics. The third is Lang. I have Goldstein, by the way, second edition, which the professor apparently likes the most. It looks like this. If anyone wants to buy it. By the way, you can get these books online. I'm sure you know where to find them. I mean, with the PDF for free. I cannot say it loud here, but if someone doesn't know the website or anything, just write to me. Okay. This is called variational principles of mechanics. Fourth is Hand and Finch, called analytical mechanics. Okay, I should write this full analytical mechanics. Fifth is by Pars, called analytical dynamics. Dynamics. And the sixth one is Arnold. Oh, this is some treatise on analytical dynamics, something. This is called mathematical methods of classical mechanics. I personally haven't seen these two, so I don't know, but professor says it might be advanced for some of us. I'm including me because even I don't know how difficult it is. But you can take a look at it. So these are the books. Now questions, comments, anything? Someone. Oh, Meenakshi said, sorry sir, I couldn't unmute. That's okay. If you have any questions and you want to type in chat box, now I can see it. So you can write. So nobody has any questions from the lectures, something that didn't understand? If that is the case, then I must congratulate Professor Tripathi. He has done very good job in explaining. Any comments, Raku?
Let me just go through my notes and check things.
Sure. Harish, you have any further questions, comments?
No, sir.
Okay. Thank you, sir. Excellent session. Thank you very much. That means a lot. Ideally, we have 2 hours of time, but okay, if there are no more questions, maybe we can say goodbye.
In the book,
Yeah,
Goldstein,
yeah.
uh, there's also the Hamilton approach for the Lagrangian. Are we not covering that approach in this course?
You're talking about the least action principle, Hamilton's
Yes.
principle.
Yes.
I think it's there towards the end of the course.
Oh, I see. Because it was introduced in the first, second chapter in the book.
That's how it is generally introduced in most of the courses and the books. But for some reason, Professor Tripathi has kept it at the end. But we will have it. Yeah.
Okay.
Yeah.
So one question about the D'Alembert principle. This is, uh, in essence, just a restatement of Newton's second law, right?
It's a restatement of Newton's second law. Um, I mean, yeah, deriving it would require you to use Newton's second law. Would you call it restatement? I mean, yeah, sure. You can say Newton's laws with surfaces taken into account. Yeah.
Okay, surfaces, surfaces as in, could you elaborate on that?
So when we say Newton's law, I mean the second law, we write it as F is equal to ma, or rather dp by dt. That's more proper way of saying it. So there, F is just the external forces in the given particle, and p is the momentum of the particle, right?
Yes.
Yeah. So that is when there are no constraints on the particle. But let's say the particle can only move on a surface of a laptop. Let's say. And then in that case, because of that constraint, the particle will experience the force that is not coming from any external agent, like the earth pulling it down or anything. It's just that because the particle has to stay within that surface, uh, there will be some effective force of the surface, right? So that's how we write F, that is the external force, plus small f, that is coming due to constraint.
Okay, so but here it's more of a mathematical construct, or is it
It
a
is
physical?
mathematical, yeah. So when we say surface, it need not actually be a physical surface, right? It's a surface in the space of the coordinates. So it could be that if they are, let's say, two particles connected by a rigid rod, then what's the surface? Surface is the equation mod r1 minus r2 is equal to constant. So that is one surface. In where is that surface? Is it in the physical space? No, because both r1 and r2, we have to put it in the same space. So actually, it's an equation in 6 dimensions, right? So it's a surface in 6 dimensions.
Okay.
Yeah, but there is a force due to that surface or the constraint, which is not present in the Newton's statement. So, okay, so that's the difference between them. But yes, they are not contradictory. And the D'Alembert principle uses F is equal to ma. Yeah. Okay. Okay. Anything else? Anyone? Okay. I
I
have a
saw an
question.
example. I saw an example in the Goldstein book of that
Mm-hmm.
Atwood's machine.
Atwood machine. Yeah.
It's basically two masses suspended on a pulley.
Right.
So here, Goldstein remarked that we found the equation for the acceleration without considering the tension in the rope, in the wire.
Yes.
Yeah, so using just the expression for the Lagrangian and thereby the kinetic and potential
Right,
energies.
right. So that's true. So that's why people like Lagrangian, because once you write the Lagrangian, you don't have to worry about forces. You know what is the force due to the string, what is the force due to this, and what is the component along x-axis, and equate them, everything. All those information is are kind of hidden, incorporated into this one scalar called Lagrangian. So it's like a very finely packed function, you can say. So to answer your question, the tension, yes, we don't use what is the tension, anything, but we did use the fact that the length of the string is constant. So if you see the solution, one is x, another is L minus x. So when we wrote that, we incorporated the fact that the tensions will take care of uh, those masses not just falling down. So by writing x and L minus x, we incorporated the tension.
Oh, I see.
Okay, yeah,
That's very nice indeed.
it's very nice. Yeah, more you deal with Lagrangians and Hamiltonians, more you tend to appreciate.
Oh, but it also mentions we can't find the tension in the rope directly by the Lagrangian method, I
Yeah,
guess.
we cannot, but we'll see in future. I think it's there. We can calculate it by introducing something called Lagrangian multipliers. So I think we will do that in future, probably towards the end. Okay. Okay, one question. I today covered some, I did some brief recap of the week. What did you think of it? Anyone can answer. Like, is it a good thing, or should I continue it? Should I modify it or omit it?
Yes, sir. It's a good thing. You can continue doing it.
It's a good thing, yeah? Okay. And if you want me to do something else also, you can just tell me.
I think it would be nice if we could have more uh, derivation type questions, which will help us apply the concepts, like
Okay,
the last extra questions, instead of MCQ type.
I see, I see. Okay, and then I'll try to add more questions. Uh, the only thing is that what we were told by the NPTEL team was that solve only the questions from the previous assignments, because we don't want to solve your current assignments by any chance. So, but I can understand there were just two questions from the previous assignments. So next time I'll add more questions. Yeah, that's a good suggestion. Thank you.
Sir, unfortunately, these two questions are there in the right present assignments as well.
Sorry, can you repeat? It's not very audible.
Questions that you solved are also in the live assignments.
Really?
Yeah.
Oh man, I should have checked live assignments. For some reason, it's very difficult to log in to this thing. Do you face a problem with logging into NPTEL?
No, not at all.
No?
No.
Me
Um,
neither.
okay. Okay, next time I'll take care of them.
I log in using Swayam. Which one do you use?
Okay. No, we are given one special reviewer account, but it says you you cannot log in or something like that. Then you have to go to incognito. But even then, it didn't work this time. And then Okay. Next time I'll take care of. Thanks for letting me know. Anyways, I think only 12 or 13 people joined, so they should get some reward for joining. So that would be my excuse.
Yes.
Yeah. So how many questions do you have this time?
It's only 5 for the second assignment.
5, right?
Yeah.
So
And each carry 2 marks.
each carry 2. That's okay. And are they easy or difficult? How do you find them?
Until this point, I find them easy.
Hmm. Yeah.
I don't know.
You are a master student, right?
No, I'm a BTech student
BTech, where?
at NIT Trichy.
NIT. Yeah. Yeah, the thing is, these courses are for everyone, even though they are advanced. They're supposed to be accessible for everyone, so they can't keep it too difficult, I guess.
Yeah, but I expect the course will get a little bit harder in the end. So I'm happy I took this.
Uh, maybe it will, maybe it won't be, but the thing is, I think content is quite not hard, but it requires time, especially if you are doing it for the first time. It's just that they keep assignments simple because they don't want to, just scare people away from taking courses because of that.
Oh, understandable.
Yeah, yeah. But if you want to do hard problems, you can always go to Landau or Goldstein. Or you can find problems online as well. Okay. Meenakshi ma'am is saying good, it's good going. I guess it's about the recap. Yeah, thank you for the feedback. Okay, so if there are no more questions, then we'll end. We'll meet next week, same time, hopefully. Okay?
Thank you for this
Yeah.
discussion.
Bye.
Thank you for the question, sir. Bye.
Bye.